Okay, so just to finish up this question, remember to label your graph, and we labeled it based on the original function. It doesn't matter which function you use, the factored one or the original one. And we're going to look at the domain and range. So looking at the domain, the graph continues infinitely to the left and to the right. So I know the domain is x such that x is an element of all real numbers. And the range, because the graph was not reflected in the x-axis, so because the graph is still above the asymptote, I know the values of y that I have must be greater than the asymptote, which is at -4. So the range is going to be y such that y is greater than -4 and y is an element of all real numbers. The equation of the asymptote relating back to the vertical shift down 4, I know the equation of the asymptote is y equals -4. And in terms of the restriction, I know we didn't look at this in too much detail. You don't have to worry about it too much anyway. In terms of the restriction, it just means what value of y can you not have. And in this case, y cannot equal -4, or y cannot be less than or equal to -4. That's another way of actually looking at it, because you can't actually have values of y that are less than -4 as well. Okay? And then is the function increasing or decreasing? Look at the graph from left to right. Are the y values going up or are they going down? And in this case, because they're going up, we know that the function is increasing. Okay, let's take a look at example 2. Example 2 is an application question. And remember that you are going to have some application questions on your test, so you want to make sure you review some applications as well. And so this question says there are initially 5,000 bacteria in a culture. The number of bacteria doubles every 2 hours. So you're told that the initial population is 5,000 bacteria and that the number of bacteria will double. Okay, so that should help you figure out what the ratio is going to be. Doubling means that the quantity is going to increase. And so that tells me I'm going to have a growth ratio of 2. It's doubling each time. And it tells you how often it happens, every 2 hours. So this will help you with the exponent part. So it says write an equation that models the number of bacteria in a culture after t hours. So start with y equals a times b to the exponent x, since we know what each of these represent. And because my dependent variable is the number of bacteria, and my independent variable is the time in hours, I can write that b of t, so the bacteria over time, is equal to, a represents the initial quantity, so that's 5,000. B represents the growth or decay ratio, and in this case it's a growth ratio of 2 because it's doubling. That's what I need to multiply each time. And in terms of my exponent, I'm looking at t hours, but the way I've written it right now, it looks like it doubles every hour. But I know that based on the question, it only doubles every 2 hours, so I need to make sure I have my division by 2 here. So there's the equation. T is in hours, B represents the number of bacteria. Then it says how many bacteria are present after 1 day. So remember that we have an equation that we can use to help us solve this problem. I can sit there and do it manually, but that'll take a really long time, and that's not an efficient way of doing the question. And so it's very tempting to just plug in t equal to 1. However, our time value are in hours, so we need to make sure that we convert 1 day into hours. So that means t is going to equal 24 hours, since there's 24 hours in a day. And so I'm going to look at the number of bacteria over a 24-hour period. And I get 2 to the exponent, 24 over 2. And I can actually simplify the exponent part without getting a nasty decimal, so I'm going to do that. And I get 5,000 times 2 to the exponent, 12. And this makes sense because in 24 hours there should be 12 doubling periods. So let's calculate that quickly. We get 5,000 times 2 to the exponent, 12. And I get a whole lot of bacteria. And that's 20,480,000 bacteria. That's a whole lot of nasty bacteria in a very short period of time. Okay, so therefore, there are 20,480,000 bacteria after 1 day.